From UFOs to possible alien abductions, we're fascinated by the idea of extraterrestrial life. Now, scientists have found the strongest evidence yet that a planet 124 light years away could be home to life.
When the James Webb Space Telescope was launched, the world knew it was about to witness a new era of astronomy. What we didn't expect was how quickly it would start delivering data that could change the way we understand our place in the universe. Among its most groundbreaking findings are early signs that may suggest the presence of life on distant exoplanets, planets orbiting stars far beyond our solar system. This isn't science fiction anymore. This is the cutting edge of observational science, and the results are nothing short of astonishing. The James Webb Telescope, often shortened to JWST, was launched in December 2021 as the most powerful space observatory ever built. Its primary goal was to peer deeper into the universe than ever before, to explore the formation of stars and galaxies, and perhaps most excitingly, to examine the atmospheres of exoplanets for signs of habitability or even life. Using infrared technology, Webb can analyze the composition of an exoplanet's atmosphere by studying how starlight passes through it as the planet transits in front of its host star. This technique, known as transmission spectroscopy, has allowed scientists to detect specific gases in exoplanet atmospheres. Some of these gases are biosignatures, indicators that could suggest biological processes at work. Recently, the JWST turned its gaze toward a handful of intriguing exoplanets, and the data that came back has stunned scientists worldwide. One of the most talked about targets is a planet known as K218b, located about 120 light-years away. In the constellation Leo, this exoplanet lies within the habitable zone of its star, the region where conditions might be just right for liquid water to exist. K2-18b is classified as a mini-Neptune, meaning it has a thick atmosphere and is larger than Earth, but smaller than Uranus or Neptune. Until recently, scientists weren't sure whether such a world could support life, but the James Webb Telescope is rewriting those assumptions. In its analysis of K2-18b, JWST detected the presence of carbon-bearing molecules like methane and carbon dioxide. Even more intriguing was the potential detection of a molecule called dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by biological processes, specifically by phytoplankton in the oceans. While it's far too early to confirm the presence of life, the very hint of DMS on an exoplanet is a jaw-dropping revelation. It's the kind of clue that makes scientists sit up straight and say, "Wait a minute, what are we really looking at here?" The significance of finding methane and carbon dioxide together is also noteworthy. These two gases can exist independently in many planetary environments, but their specific ratios and coexistence can point toward biological activity, depending on the temperature and atmospheric pressure. On Earth, for instance, methane is constantly being produced by living organisms, and its presence in the atmosphere is balanced by processes like oxidation. Seeing similar dynamics elsewhere could suggest that something more than just geology is at play. Another exoplanet that caught scientists' attention is TRAPPIST-1e, one of the 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1, located 40 light-years away. Webb's early observations of this system have already provided tantalizing clues. Although the telescope hasn't yet confirmed biosignatures on TRAPPIST-1e, it has shown that the planet may possess a relatively thin atmosphere with potential for water vapor. Given its size, density, and position in the star's habitable zone, this planet remains one of the most promising candidates for hosting life as we know it. The possibility of water on exoplanets is essential, not just because water is a key ingredient for life, but because it could serve as a medium for biochemical processes, similar to those on Earth. Webb's infrared sensitivity allows it to detect water vapor in the atmospheres of planets tens or even hundreds of light years away, and some of the exoplanets studied so far are showing early signs of this critical element. Of course, the discovery of potential biosignatures is just the beginning. Scientists must rule out all non-biological explanations before making any definitive claims. That's part of what makes the JWST's work so meticulous. Researchers use computer models to simulate planetary atmospheres and compare those models to the data collected by the telescope. If the models without life don't fit the observations, and the ones with life do, then that becomes a compelling argument for biological activity. But the Webb telescope is not working in isolation. Its findings are often followed up by ground-based observatories or previous data collected by the Hubble Space Telescope and the now-retired Spitzer Space Telescope. Together, these observations are helping scientists build a more complete picture of these distant worlds. What's especially exciting is that we're still in the early days of JWST's mission. Its instruments are still being calibrated, and only a fraction of its observing targets have been analyzed in depth. Yet already it has returned data that makes scientists rethink old assumptions about where life might exist. One fascinating implication of these discoveries is the potential diversity of life itself. If biosignatures are found on planets very different from Earth, such as mini-Neptunes or tidally locked planets, then that could mean life isn't limited to Earth-like conditions. Maybe life can thrive in high-pressure atmospheres, beneath thick clouds, or in oceans hidden under layers of ice. JWST's discoveries are helping to stretch our imagination and expand the definition of habitability. Equally important is the fact that JWST is also finding planets that are likely not habitable, which is just as valuable scientifically. For instance, by analyzing the atmosphere of a super-Earth called GJ486b, scientists discovered that its surface is likely too hot to support life, despite being a rocky planet. These negative results help refine our models and guide future searches toward more promising targets. As the telescope continues its mission, more observations are scheduled for other potentially habitable exoplanets like LLHS 1140b and Kepler 442b. Each of these planets has its own unique properties. Some may have thick atmospheres, others may have oceans of lava, and some might even have clouds or weather systems. The sheer variety is staggering, and Webb is just starting to peel back the layers. The excitement around biosignatures doesn't just come from scientists. Governments, space agencies, and the public are all paying attention. NASA and the European Space Agency have emphasized the importance of JWST's role in the search for life, and the possibility of detecting life beyond Earth is no longer considered fringe or speculative. It's becoming a mainstream scientific pursuit. The growing interest in exoplanet research has also given rise to entire new fields, such as astrobiology, planetary climatology, and atmospheric chemistry. Each new transmission from the James Webb Space Telescope fuels new hypotheses about how life might develop in alien environments. Researchers are rethinking the very definition of life, expanding it beyond the Earth-centric models we've traditionally used. What if alien life doesn't rely on water or oxygen? What if it breathes sulfur, thrives in high-pressure environments, or lives beneath the surface of a frozen world? The possibilities are endless, and Webb's discoveries are pushing scientists to consider them more seriously than ever before. A crucial technique used by JWST is the analysis of light curves, the change in a star's brightness when a planet passes in front of it. These subtle dips allow scientists to not only calculate the planet's size and orbit, but also analyze starlight that filters through the planet's atmosphere. This filtered light is broken down into a spectrum, revealing the chemical fingerprints of gases like water vapor, methane, carbon dioxide, and possibly even ammonia or oxygen. It's an indirect way of reading the atmosphere of a world light years away, but it's surprisingly powerful. One of the most fascinating observations so far came from a planet called Bayou ASP-39b, a hot gas giant. Though too extreme to host life, its atmosphere was found to contain sulfur dioxide, a product of photochemical reactions caused by stellar radiation. This marked the first time such a process had been confirmed on an exoplanet, showing that even in harsh conditions, complex atmospheric chemistry is at work. These processes, while not proof of life, set the stage for how molecules might evolve into life-giving compounds under the right circumstances. The sheer sensitivity of the James Webb Space Telescope is part of what makes these discoveries possible. Its giant gold-coated mirror and its cutting-edge infrared sensors allow it to detect even the faintest signals from distant worlds. Unlike telescopes that work in visible or ultraviolet light, Webb specializes in infrared, which is ideal for studying cooler objects like exoplanets, and allows it to see through the dust that blocks other forms of observation. This makes it perfect for studying both young planetary systems and mature ones that might be home to life. Importantly, the scientific process demands caution. Methane or carbon dioxide alone do not confirm the presence of life. These gases can be produced by volcanic activity, photochemical reactions, or other non-biological processes. That's why scientists look for combinations of gases that shouldn't coexist unless something is constantly producing them. This concept, known as atmospheric disequilibrium, is one of the most promising strategies for identifying life. On Earth, for example, the constant presence of both oxygen and methane is only sustainable because living organisms keep producing them. Using this approach, researchers create atmospheric models of exoplanets. These models help determine what chemical mixtures could be produced by geology, by photochemistry, or by biology. If a planet's actual data doesn't match what's expected from natural, lifeless processes, that inconsistency could point towards something much more intriguing. It's a methodical, step-by-step process, but one that brings us closer to a definitive answer. Another exciting development is JWST's growing ability to assess surface conditions. Though we can't yet see the surface of an exoplanet directly, scientists are using data from Webb to estimate surface temperatures, pressures, and even the likelihood of oceans or continents. These insights come from studying the way energy is absorbed and emitted by the planet's atmosphere. Some exoplanets might be water worlds, others rocky deserts, and some potentially Earth-like. These evaluations help prioritize future observation targets and build detailed profiles of alien worlds. There is also an emotional side to all this. The idea that we might be witnessing the first evidence of life beyond Earth is deeply moving. For centuries, people have looked up at the stars and wondered if we are alone. Now, for the first time, we are gathering the kind of data that could actually answer that question. It's a profound moment in human history. The implications reach far beyond astronomy. They touch philosophy, religion, ethics, and the way we see ourselves. If life exists elsewhere, it suggests that life is not unique to Earth, and that the universe may be filled with other living worlds, other biospheres, and perhaps even other civilizations. As new data flows in, scientists are becoming more selective in choosing which planets to study in detail. Not all exoplanets are equal. Some orbit stars that are too volatile, others are tidally locked with one side permanently scorched. But with each observation, the list of potentially habitable worlds grows. Planets like LHS 1140b, Kepler 442b, and K23d are being closely studied, each showing hints of the conditions that might support life. And JWST is not working alone. It's part of a broader scientific effort. NASA's upcoming Roman Space Telescope and ESA's ARIEL mission are set to launch in the coming years. these missions will complement JWST by surveying thousands of exoplanets, identifying candidates that Webb can then study in greater detail. It's a coordinated, layered strategy designed to maximize discovery potential. In the private sector, initiatives like Breakthrough Starshot are exploring the possibility of sending tiny probes to nearby stars like Alpha Centauri. The excitement surrounding exoplanets is no longer limited to government space agencies. It's becoming a global endeavor. One of the most thought-provoking ideas is that life may be more common than we ever imagined, and that our tools just haven't been powerful enough to detect it until now. As JWST continues its observations, the dream of finding life beyond Earth inches closer to reality. Whether it's microbial life, simple organisms, or even advanced biospheres, any discovery would be groundbreaking. And it wouldn't just change science, it would change everything. Of course, we're not quite there yet. The signals detected so far, methane, carbon dioxide, dimethyl sulfide, are incredibly exciting, but they are not conclusive. Scientists are carefully analyzing the data, checking for alternative explanations, and planning follow-up observations. The next few years will be critical. As more planets are studied and more biosignature patterns are confirmed, we may move from speculation to confirmation. The moment that happens, the world will never be the same. Even now, the signs are pointing in a direction that is hard to ignore. Webb has shown us that planets with potential for life are not rare exceptions. They are plentiful. Life may not be the miracle we once thought. It could be the cosmic norm. The universe might not be a barren void, but a vibrant expanse filled with biology, chemistry, and evolution, playing out in countless unique ways. So, as we continue to analyze the light from distant stars, study the chemistry of alien skies, and search for that unmistakable signal that confirms we are not alone, we are witnessing one of the most profound scientific efforts in human history. The James Webb Space Telescope is not just a machine, it is a gateway to a new era, one where the question of life beyond Earth is no longer a mystery, but a matter of time. We are no longer just asking if life exists elsewhere. We are searching for it with precision. We are scanning atmospheres, reading light spectra, interpreting strange chemical fingerprints. We are narrowing in on the truth, and with every transmission, every observation, and every discovery, we are moving one step closer to answering the greatest question ever asked by humankind.